Welcome to Pomodoro Joe for Saturday, March 25th, 2023. Today we're doing LeetCode problem 2316. Count unreachable pairs of nodes in an undirected graph. It's a medium problem. You are given an integer n. There is an undirected graph with n nodes numbered from 0 to n minus 1. You are given a 2D integer array, edges, where edges index I equals AB, denotes that there exists an undirected edge connecting nodes A and B. Return the number of pairs of different nodes that are unreachable from each other. That's interesting. Return the number of pairs of different nodes that are unreachable from each other. Oh, okay. So let's look at some examples. So in this first example, there is one set of nodes that are all connected, so the answer should be 0. And yep, looks like we return 0. Okay, example 2. Okay, it looks like we have sort of 3 distinct graphs. One with 1 node, one with 2 nodes, and one with 4 nodes. So if I were to calculate the number of distinct pairs that are not connected, that would be this graph times 1, 2, 3, and 4. And then again times 1 and 2, because there are 4 unmatched pairs with this first graph and 2 unmatched pairs with this second graph. So that leads me to 6 pairs for this node, or graph, I should say. And then how many for this one? Well, there's 1, 2, 3, 4 for node 1, and 1, 2, 3, 4 for node 6. So that's 8 in total. So we had 8 plus 2 plus 4 should be 14. Yep, we return 14. Okay. Now it looks like to find the pairs of unmatched nodes is basically the same as just saying how many nodes are in this graph and multiply that by how many nodes are in this graph. So let's see if that works out. So if we take graph, let's call this graph A, B, and C. So graph A times B, that's 1 times 2 is 2. And then 1 times 4 is 4, so that's a total of 6. And then 2 times 4 is 8, and 8 plus 6 is 14. Yeah, so that works out. And no more examples. We got some constraints. Okay, so I'll put 25 minutes on the Pomodoro timer and we will get started. So first I will have some result and we'll set it to 0 to start with. And at the end we will return our result. So for this, in the examples, they already sort of broke out the nodes into these subgraphs. So I'll follow their lead and do the same. We'll go through all of these edges and we'll try to figure out these subgraphs of all of the nodes. Once we have all of these subgraphs, then we can just go through, find their lengths, and multiply them all together to get our answer. So that's the approach I'll take here. So let's see, let's write some pseudocode here. So we need to find all the subgraphs. And then once we have all the subgraphs, we have to find their result by multiplying the subgraph lengths. Okay, so finding all the subgraphs, that's going to be a little bit tricky. So the first thing I think I'll do is let's convert these edges into something a little bit more usable. So let's have some set of, let's see, what's the best way to do this? Yeah, we'll have connected nodes. Here we go. And it's a default dictionary of sets. So our connected nodes, the key will be our node, and the value will be all the nodes that you can reach from this node. All right, so for every edge, we'll call it AB in edges. So A is one node, B is next node. As you can see in the example here, every edge has 2 nodes. So let's see, that means our connected nodes at A, I'll just copy this. We'll just add B. And same thing for connected nodes at B, we'll add A. So now we've got a dictionary where the key is a node and the value will be a set of all the nodes that you can reach from this node. That's going to be super useful. Now let's see, how do we find all the subgraphs? Let's just pass on this for now. Okay, once we have all the subgraphs, let's just have some array of graphs here. Then once we have all of the graphs, we can say, let's see. Well, we'll do this the straightforward way first, and then we'll do this in sort of the optimized way next. So the straightforward way here would be for every index in the range of our graphs, we'll grab the current graph. And now we need to find all of the other graphs and their lengths. So let's see, let's get the length of the current graph. Now we need to go for every j in range. Now we'll need to go from our current I plus 1, because we don't want to include our I itself. But we still need to go to the length of graphs. So it looks like I need to actually add that here. Now the next graph is going to be the graph at j, and the next graph length, with the length of that next graph. And let's see, finally, we will multiply. Let's see, our result will be increased by the current graph length. Times our next graph length. Okay, I am going to have to pause this here. Someone's at my door, which is very strange. And I'm back. That was weird. So, my neighbor's car is parked out in front of my house pretty much permanently on the street, and a delivery driver accidentally backed up and scraped it. And so he's knocking on my door to let me know, because he thought it was my car. That was nice of him. So I gave him a pen, paper. He's writing a note to the owner of the car. But, all right, let's get back to it. All right, let's see. Now we increase our result by the current graph length times the next graph length, and we do that for every graph. Okay, now we still need to find our graphs. So let's see, how do we do this? Well, we'll say for every node in range, oh, I can't use n, for every node in range n, because we know that there are n nodes labeled from 0 through n minus 1, we'll just have this, like, we'll say graph dot append. Well, let's see, I'll do graph is equal to, let's make some function called graph for node, and we'll pass in that node. And then we'll add this graph to our graphs. We might end up, if we have nodes that are in the same graph though, we might end up appending the same graph multiple times. Let's say we get node 0, we'll get this whole graph, and then we go to node 1, we'll get this graph, then we go to node 2, we'll get this whole graph again, which we don't want. So we need to keep track of which nodes we've already gotten graphs for. So let's have some visited. Let's do this. It'll be a set. Oh, we can actually, I thought about it. We can do something even more clever. We can say false times n. So now for every node in range n, if visited at this node, then we'll just continue. We've already got a graph for this node. Okay, now we need to define this graph for node. All right, well, let's do that up here. So this will be the root of this graph. So this is going to be pretty much a standard depth first search or breadth first search. We're just going to find all the nodes that are connected to this node and put them into a graph. So let's see, we'll have some graph. We'll start it as an empty array. We can make it a set. Yeah, let's do that. make it a set, and we can return our graph at the end. Okay, so with a standard depth first search or breadth first search, we'll have some queue of nodes, and we'll start with the root node in our queue. So this type of problem you'll find a lot in LeetCode. These are going to be problems where you have some graph, you need to basically start at some root node, find all the nodes that are connected to that node, and then go visit all of those nodes, finding the nodes that are connected to those nodes. So typically you'll use this in a depth first search or breadth first search. This is something that you find so often, it is so common that I highly recommend studying this basic formula for either doing a depth first or breadth first search. The idea is you have some queue of nodes that you need to go to. So these are all the nodes that you haven't processed yet, but you do need to process, and you'll start with your root node. Then you need to have some list of nodes that you have already seen, so you don't end up going in circles, basically. So we'll just use this visited up here as our way of tracking which nodes we've already visited. And then we need some output, which is going to be a set of all of our connected nodes. Okay, so now while we have some nodes in our queue, so in our case we can just say while queue, well, we'll grab the first node. Then we check to see if we've already visited this node. If we visited this node already, then we'll just continue. Now, if we haven't visited this node, we'll need to make sure that we visit the node by setting visited to true. And then we need to find all the nodes that are connected to this node. Now, luckily we have this connected nodes that we created up here, so we can just grab that and use it. So for every next node in our connected nodes for this node, we're just going to add these nodes to our queue because we need to process them. Now let's see. All right, and then we want to add this node to our graph as well. Actually, let's add it to our graph when we visit it. So we visited the node, now we'll add it to our graph. All right, so that should give us the graph for this root node. Okay, so let's go through our algorithm one more time. So we've got all of our connected nodes in some dictionary here. Then we go through and we'll find all of the graphs for all of our nodes. Once we find all the graphs, then we'll go through every graph and try to find its length and multiply it by all the other subgraphs in our list of subgraphs, and we'll add that finally to our result. Wow, that's a lot. Let's see if this works. All right, this should be graphs. No, we made graph a set, so this should be add. All right, try that one more time. Okay, it seems to work. Let's see if we can pass all of the runtime requirements for this one. I have my doubts, but we'll see. And we don't, but we get pretty close. We beat 56 out of 66 test cases. So it means we're on the right track. We didn't get any wrong answers. We just didn't do this fast enough. So we're on the right track. We just need to speed this up. Well, let's see. Where can we speed this up? We can't really speed it up in getting our connections. That's pretty much as fast as we can go. We might be able to make some minor improvements, but nothing major here. Let's see. Finding all the subgraphs. This one, there are ways to speed this up, but I don't think we're doing too much work in here. Like, this seems pretty straightforward. The place where I think we can get the greatest improvement is on this finding the answers here. This has a for loop in a for loop. That's generally a sign of slowness. Basically, you'll be doing for every I, j additional operations. It's slow, let's put it that way. So one way we can optimize this is, if we think about it, we're basically saying, let's see if I can show the math part of this. So we have, let's see, 3 different graphs, A, B, and C. And so let's say those are the lengths of our graphs. So for the first one, we're saying it's A times B plus A times C. So these are lengths. And then for our second one, it's just going to be B times C. Well, we can factor this A out of this. That's going to be the same as saying this is A times B plus C. Now, if we did that, let's say we had A, B, C, D, E. We had a whole bunch of these things. A, B, C, D, E. Instead of having multiple embedded loops, we could factor out all of the common multipliers. So we can have A times basically B plus C plus D plus E. And then we'll have B times C plus D plus E. And we'll have C times D plus E. The other thing that I see in this pattern is we have this addition. This C plus D plus E contains this addition. And this addition up here contains this addition. So it looks like what we can do here is just add, let's say, A plus B plus C. So we can just add all of the lengths of our graph together. Then we can pull out one at a time, A, and multiply it by whatever remains. Then we pull out B and multiply that by whatever remains, and C and D and so on and so forth. So I think we can remove this inner loop and just do a single loop through all of our graphs. Let's give that a shot. So the first thing we'll need is have a total length. So that's going to be the sum. Let's see, we need to get all the lengths of our graphs. Well, let's do it this way. Okay, so we'll get the length of every graph for the graph in our graphs array, and we'll just get the sum of that. So the total will equal the sum of graph lengths. Okay, so now instead of doing all of these internal loops, we can replace this whole thing by saying for, let's see, yeah, for every graph length in our graph lengths, our result will increase by, let's see, we need to decrease our total first. So we'll subtract this graph length from our total, and then we'll increase the result by this graph length times the remaining total. I think that's it. So this set of code replaces this entire set of code here. Let's get rid of that and try this again. Still works. Let's see if we can pass the runtime requirements now. And we pass. So we don't do great. We beat 29% for runtime and 39% for memory, so not great. Let's see if we can improve on this. We still have 6 minutes. Yeah, let's see what we can do. So in this breakdown, we broke this down into finding all of the graphs first and then going through and finding the result. What if we did this part, this finding the result, as we find the graphs? Because we don't actually need to keep the graphs. We just need to know if we visited nodes, and we need to know how long the graph is. So instead of returning the graph here, we can return the length of the graph. And then instead of just adding it to our graphs here, we can increment our result. So let's do that. All right, so our total graph lengths will start as 0. Now instead of returning the graph here, let's return the length of our graph. And so this will be graph length. And then we don't need this graphs anymore. All right, and so then we can increment our result by this graph length by our total graph lengths. So this is doing the same thing that this is doing. It's only doing it, I guess, in reverse order. And then we need to add our new length to our total graph lengths. All right, so that should eliminate this whole loop here. Let's see, I still need a result though. Let's see, yep, that's still good. Okay, so now as we get our graphs, we're gonna just grab the length right away and we'll increment our result or include that new length times the existing graph lengths in our result. Then we'll increase our graph length by the new graph length. I'm running low on time, so I don't know if we'll get this done by our Pomodoro, but we'll see what we can do. Okay, that works. Let's submit this, see if we get any improvement. And we do. Now we're at 51% for runtime and 39% for memory, so that is an improvement. Still looking for a 90%, but I am down to 2 minutes. I don't have time to optimize this anymore. But if I were to optimize this, there are two things I would do. One, I would see if I can include this whole thing inside of our depth first search. The other thing I might do is completely throw this entire thing away, and instead of doing our depth first search, we can do something called a union find. Now that's a much more complicated, well, I shouldn't say more complicated, but it is a different algorithm altogether. It's a little bit rarer, you don't find it as often, but it would be useful in a case like this. You can check that out. I will maybe leave some links in the description. I'm running super low on time today, so I don't know if I will. But that's it for me. Hope you enjoyed this, hope you had fun, hope you learned something, hope you can go out and write better code.